name is Michael Aling. My PI is Dr. Stephen Wilson, and my mentor is Dr. Julian Schmer from the Materials Science Department at UCSB. And this summer I've been working on investigating the magnetic transitions in a doped Mach insulator in order to understand more about the compound. So materials science is a very broad field. It has a lot of subdisciplines that are very prominent and have been in headlines in recent years that I'm sure you've seen, because there's been a lot of growth in these fields. I specifically work in the electronic and magnetic materials subdiscipline, which includes everything from semiconductors, which have revolutionized the electronics industry in the past, to superconductors and more advanced items, which promise to do the same in the future. We also mesh increasingly with condensed matter physics in order to study more magnetic and electronic phenomena that were not previously available for study. We work on a small scale in a lab, growing our crystals and measuring various properties about them in order to better understand how they could be potentially applied for things like the modern computing industry, for solid-state devices, and for the next generation of electronics. These take place on a large scale. You can see that our crystals that we grow are about 1 millimeter square. This crystal here is about 2 meters long. What we find in the lab today can determine what the electronics industry can produce 20 years down the line. These are the crystals that I'm working with. They're strontium-3, iridium-2, 07. They're interesting because the strontium-3, iridium-207 is a Mach insulator, which has some interesting quantum physics going on. And then there's a cousin compound, strontium-3, ruthenium-207, which is metallic and also exhibits a number of different properties. So as you dope, what I'm doing is doping ruthenium into the compound, which is replacing the iridium with ruthenium atoms. As you do that, there's necessarily a metal insulator transition between the two compounds I mentioned. This varies with temperature as well as with dopant level. There's a second transition that we also study. It's a magnetic transition between paramagnetism, which is essentially a disordered magnetic state, and an antiferromagnetic state, which is one in which adjacent atoms have oppositely aligned magnetic moments. Their magnetism points in opposite directions. This also varies with dopant level and temperature, and as you can see, the more ordered state tends to be lower down in temperature, which makes sense because as things settle towards 0 Kelvin, they tend to a more ordered state. When you put the two transitions together, you end up with a phase diagram that looks something like this. Each bounded region is its own phase, as shown in this diagram, which also includes the data points taken by a previous study in our lab. An interesting fact about this material that makes it different from other materials is that the metal insulator and magnetic transitions are not homogeneous through the entire material. On a nanometer scale, there are competing subregions with different properties. So for the metal insulator transition, for instance, there are metallic regions and insulating regions coexisting very close to each other. And the material only becomes metallic when the metallic puddles grow large enough that they can form a conducting network across the compound. The same thing happens with the magnetic transition, but there are some interesting complications in that the proximity of the antiferromagnetic material to the paramagnetic material means that the antiferromagnetic material can instill order upon the disordered paramagnetic material. This increases the overall antiferromagnetism when you would otherwise expect it to smoothly decline down to 0 at a certain point. After a certain point, there's little enough antiferromagnetic material to begin with that the antiferromagnetism dies off completely. That's what I just mentioned. So, as you can see, the right-hand side of the magnetic transition line has not been very thoroughly studied. We don't know its shape very well yet, and we don't know very much about the compounds in the region below that line. I mentioned a reason that we believe is the cause for the upturn, but we have not thoroughly investigated that, and that's one of the things we hope to investigate this summer and in future months. And there's also a mystery about what happens at low temperatures along the magnetic transition line. When you have two competing magnetic phases, sometimes at low temperatures along the boundary between them, the compound likes to settle into a new state. And this new state can be something like a superconductor, or it could be another magnetic phase or electronic phase. I mentioned superconductors because several other compounds related to this compound do settle into superconducting states at low temperatures. Or it could be nothing at all. That's always the case with science, but we won't know until we look. And our goal is to study the antiferromagnetic, in addition to looking for a new phase, is to study the antiferromagnetic metallic region and the overall shape of the transition line, so we will be able to tune these crystals to have the properties that we want. In order to to do this, we first recreated prior dopant levels that were studied in a previous paper in order to affirm that we can still replicate the process. From there, we used our experience to move into new dopant ranges in the range that we want to study, between 40% and 60% ruthenium. We performed various measurements on those in order to be able to characterize the transition line and the phases that exist around that region, and hopefully map and characterize a new phase. The growths themselves are 7-day-long flux growths. These give you a batch of crystals, which then you must, with each individual crystal, identify the purity, see if there are any contaminants, and then that is done via X-ray diffraction techniques. And the second thing that we do on them is EDX, which allows us to see what the concentration of the dopant is in the crystal, which varies pretty wildly. The measurements that we perform in order to actually study the crystals are resistivity, magnetization, and heat capacity measurements, which are all interesting in themselves, but can also tell us things about the transitions in the materials. Usually you will see some kind of feature or spike in these graphs to indicate that a transition has occurred, which helps us map and characterize the phase. So as I mentioned before, there is a very big variation in dopant levels from the crystals that you will pull from the batch. As you can see, very few are in the region that we were actually trying to grow. What you put in is not what you get out. This is because the atoms are free to rearrange during the flux growth process, so you end up with regions that are just naturally more ruthenium rich, and some regions that are naturally more ruthenium depleted. This can pose a problem if you're trying to target a specific dopant range, but it can also allow you to study a broader range in the material at once. So it's a benefit and a curse. The difficulty is that EDX measurements take a long time and are expensive. So in order to try to combat that, we've been working with a technique where we use X-ray diffraction, which is cheaper and quicker, to measure the lattice parameter of the unit cell. The lattice parameter is a dimension of the unit cell being the basic repeating pattern of the crystal. So what we're measuring is the long axis, and there's a contraction as you dope in ruthenium, because ruthenium is smaller than the iridium atoms, and the cell literally loses volume. It's a very small difference, but it is detectable. As you can see, the data points that we were able to detect via a new single crystal technique that we are trying out have matched previous data that was taken using a powder technique, which unfortunately destroys the samples you were trying to analyze. Not very useful if you're using it as a preliminary screening method. Unfortunately, the small variation that we observe in the lattice parameters means that we cannot use it in the ranges that we're looking for, because that small uncertainty can create a huge uncertainty in the dopant level. But higher in the graph, lower in the dopant level range, it could be usable in order to identify quickly the approximate dopant level that you have. It's also unusual for a material to have a non-linear contraction like this. Most will have a linear contraction, which means it would be useful throughout the graph. So one of the techniques that we use to find the actual data that we want to know is resistivity measurements. These allow us to quickly identify some basic features about the materials, such as when their transitions occur. In order to do this, you take one of your sample crystals and wire up 4 50-micron gold wires, which are attached via silver adhesive, which is conducting. You pass a current through the outer 2 leads and measure the voltage across the inner 2 leads in order to use Ohm's law to find the resistance between the 2 leads. Using some knowledge of the dimensions of your sample, you can convert that into resistivity, which is a fundamental property of the material as a function of temperature and dopant level. This is what it looks like under an actual microscope. That is one of the largest crystals we've used, and it's still only about a millimeter and a half square. So it's very fine work that has a potential to fail at low temperatures when thermal contraction comes into existence. So this is the sort of data that you would get out of a measurement like this. This is a 34% ruthenium sample, and as you can see, one region of the graph is downsloping, one region is upsloping as you approach 0 Kelvin. This indicates a transition between metallic and insulating states due to the different behaviors of those two types of compounds. You can see this more clearly by taking the derivative, where it crosses the 0 line indicates the exact metal-insulator transition. Again, this is only a nominal transition because they're insulating pockets even then. There's also magnetic transition that you can find from this data. You do this by taking the derivative with respect to 1/T, and it generates a peak where the magnetic transition occurs. This was the phase diagram when we started out our study, and we've been able to add several data points to it that indicate that our findings agree with the previous study. both the metal insulator and the magnetic transitions, as well as where we did not find a transition. This means we're ready to move on towards our goal of characterizing the other things we wanted to characterize. To reiterate, we have successfully grown several dopant levels with very low contamination, low enough that we've been able to send some to our collaborators in Korea. We've also conducted successful resistivity measurements and last parameter measurements. We are ready to move on to growing in the 50 to 70% ruthenium range and continuing our study towards our goal. We are ready to conduct new tests, magnetization, heat capacity, in order to find other features and know more about the phases themselves. And we're also able to conduct now sub-1 Kelvin resistivity measurements, which can reveal a new superconducting phase if it exists in the material, as it does in several of its covering compounds. I would like to thank my PI and my mentor, as well as CNSI and CSEP for hosting the EUREKA program, and the UCSB Department of Materials for hosting our discussion. Thank you.
Back to one of the graphs that you showed
yes. That.
Yeah, I just wanted to, I guess, what your conclusions were as to why you weren't able to complete your graph. The right concentration is kind of rare, right?
Yeah, it is rare, but once you run EDX on the samples, you do know what concentration you have. So you can then use that in order to still get accurate data points. What we have is only a partial data set. This is what was conducted with our study. The fit was from a previous study that did a similar process. And the nonlinearity is caused by, again, those competing nanometer scale regions which pull on each other in a way that is not a simple interpolation between 0 dopant and 100% dopant.
So the highest you were able to go was about 0.5?
That's the highest that we've gone so far. The highest that the previous study went is about 0.75, and we're going to be pushing into that region as well in the coming weeks.
So I guess another question I have is, if it's your parent compound is the strontium iridium oxide, does strontium ruthenium oxide exist?
Yes, it's an interesting compound for a number of reasons. It's a Fermi liquid at low temperatures, for instance, that has been studied quite significantly. It's the range between the iridate parent and the ruthenate parent that has not been studied so much. Any other questions?
Why do you need to put gold wires to do resistivity?
That's just so that you can conduct a current through your sample. That's so that is because in order to, it's easier to pass a voltage in order to create a current through the outer tube and then measure voltage on a separate set of leads. It just makes it easier for the instrumentation. Makes it more accurate.
One last question.
Yeah.
So since these materials are not homogeneous on a nanometer scale, is that inhomogeneity a problem for using it as a component in your electronics, or are those inhomogeneities still small enough?
They're literally on the scale of 1 nanometer, so at some point technology might run into that as a complication, but I don't think it would at its present state.
All right, thank you.